Jiyuan from Technion. On behalf of the team, Timson, Huaquan, Sivan, Grodsky, Davide, Schaumann, and Rafael, I would like to share our team's work on a laboratory setup for exploring digital twin construction and planning control. In the next 10 minutes, I'll briefly introduce the background of DTC, share our research goal, go through the laboratory setup, and close with the potential use case and early results. Construction today are still managed with limited situation awareness. Disruptions like defects and delay leads to inefficiencies. Decision-making are reactive rather than proactive. And DTC offers a solution. It shows greater potential to reduce waste, improve situation awareness, and enable proactive decision-making. Let's quickly clarify some definitions of DTC. A digital model is static. A digital shadow will update when there's physical changes. And the digital twin is more than that. It can react and optimize the physical system. And to guide interaction, we use PDCA cycle, plan, do, check, act, a proven structure for continuous improvement. By integrating the digital twin, the PDCA cycle, real-time project data, and more important one, the comparison between intent model and status model, we arrive at DTC. A closed-loop data-driven system enabling real-time planning control. But so far, this idea are mostly stayed on the paper. The concept of DTC was first proposed in 2020. If you're interested in more definitions, you can refer to the paper, Construction with Digital Twin Information System. And recently, researchers has developed key components of DTC framework, including the data schemas, monitoring technology, and studies explore how digital twin can support real-time control in fit-out construction. And surprisingly, there are some real case study apply DTC in real practice, but they are still in a very narrow scope. So there are still no fully operational closed-loop DTC system hasn't been tested yet, neither in industry or academia. We want to bridge this gap, and we want to prove DTC is helpful, it's indeed reduced the waste and improving the flow. To do that, our research goal to design and implement a laboratory setup to evaluate the feasibility of DTC. With this setup, we are able to build the project multiple times so that we could evaluate the performance with different planning control strategies. And this platform specifically focuses on the context of precast construction because the workflow of pre-construction is easier to monitor and track across factory production, transportation, and on-site erection stages. Beyond the feasibility, we also aim to explore the potential of this setup. For example, comparing decision-making scenarios at increasing level of automation and investigating the impact of global optimization over local optimization in DTC scenario. Okay, our laboratory setup overview. We have a physical environment, we have a digital environment. In the physical environment, we have a construction site, one builder who installed the building pieces, and one concreter who connects the building pieces, and one supplier who will manage the whole supply chain, deliver the building pieces to the site inventory. And outside the construction site, the monitoring system will continuously track the building progress, transferring and processing the data to the digital environment, to the SQL database, along with a BIM model present the status model via decision support system. And then the manager or the machine can plan or optimize the schedule and send it to the construction site, and so that we can continue to the next PDCA cycle. In the next few slides, I'll introduce the key components of our setup. The first, experimental building. It's a 1:25 scaled model of a residential building constructed in Helsinki, Finland. Our model is a 2.3 meters long, 0.6 meter width, and 0.3 meter height. It consists of 322 precast pieces made of wood as a cutting method, nearly 300 cast-in-place concrete joints, which is 3D printed plastic. Outside the model, outside the construction site, we install 4 cameras to track the building progress. A deep learning model will be running computer to detect the workers and the elements at their hand. The system consists of modules including QR code scanning, real-time image capturing, object detection, 3D localization, and visualization. All of them are running in parallel to maintain a live digital twin. And this is the output looks like. We're actually using the color of helmet to specify worker's role. To validate the system, to validate the real-time monitoring system, we choose a 10 minutes video of experiment. We manually went over around 24,000 images. And finally, we achieved like the PC detection rate is 100%, 91% for beam element matching. The position error is 54 millimeter. And we got a 1.2 seconds delay of erection finishing time. The overall matrix shows okay, well, we still have the space to improve the 3D localization process to enhance the beam element matching process. The decision support dashboard is developed using Unity. Each piece's status will be visualized using color coding, and the status of the piece will automatically update with the construction progresses. This is a time-lapse video of during the experiment. So for each experiment, we have 3 workers and 1 manager. The manager is sitting behind the window. This is the manager's working office. He will have 2 monitors, one for adjusting the schedule, one for decision support, to showing the real-time status model. Potential use case discussion. With this setup, we want to explore the potential of this setup. We want to see the different degree of automation of planning control. We want to investigate the planning performance against how much situation awareness provided. In the experiment design, we have 5 scenarios, from conventional scenario where manager receive delayed information and the paper plan, to the DTC scenario where manager have a real-time status model updated, and the decision support system will help him to pick up the best decision. Each scenario, we have 5 experiments. Each experiment lasts around 4 hours. Different managers are invited to a wide learning curve, and same objective and same constraints among our scenarios. This is the early result showcase. In the general overview, we can see that the total cost is getting lower, meaning the plan performance is getting better when we supply more and more situation awareness. If you only see the first 3 scenarios, we can notice that the variance is very big. But after the decision support system evolving in, the variance becomes small. So the technology actually flatten the decision quality and mitigate the individual differences. The limitations and advantage. Since our model is everything is performed in the lab, so the small scale setup could not fully reflect the real project complexity. And simulation limitation, since we didn't really model a factory and the road for transportation, so the factory logic and transportation logic is hard to understand at the beginning. And the advantage of our laboratory setup is enable us to rebuild the project multiple times, so that we can evaluate, we can test more and more planning control strategies and compare them. And contributions. We design and implement a laboratory setup DTC platform. We demonstrate closed-loop control by integrating real-time monitoring, digital twins, and PDCA-based feedback to support adaptive planning control. We successfully compare different level of automation in DTC system, and we can use this setup to explore more interesting topic like what is the potential of global optimization in the DTC environment. Yeah, that's all. Thank you.